distillation.
Thanks, Alex. And thanks for the nice program where Benjamin's talk nicely motivated the topic of mine.
Yeah.
So usually I have to spend some time motivating or like explaining what a resource theory is. But here I can start by talking about what the resource theory that I'm considering is. So we have an axiomatic coherent basis. And then the free states are all states that are just mixtures of the incoherent basis. So, and the free operations are supposed to map the free states to the free states. But it turns out that there is no unique way of defining the free operations to satisfy this constraint. So we can look at different possible resource theories of coherence. So if you allow all possible channels that map the free states to the free states, this is something that's called MIO, the maximal class of incoherent operations. If you impose the restriction that there must be a Krauss operator decomposition for the channel where the action of each Krauss operator is coherence non-generating, then it's something that's confusingly called incoherent operations. And then if you further restrict that the adjoint action of each Krauss operator must also be coherence non-generating, that is something called strictly incoherent operations. So you can see a lot of names here of people that are attending the conference. So operationally, you can interpret this as saying that, for example, a qubit channel that would be in the IO class, but not SIO, would be just measuring in the plus minus basis and sort of mapping the outcome onto an incoherent flat. So you can think of IO as operations where the cross operators cannot create coherence, and SIO are further restricted in not even being able to measure coherently. Of course, there's a caveat that you need to be able to measure coherently on auxiliary systems in order to implement SIO. But if you just look at the action on the space of the input, then SIO are sort of non-coherence creating or detecting. So let's look at some of the operational considerations related to coherence creation and detection. If you think of coherent measurements as some kind of primitive, operational primitive, formally you can think of it as being resource free. But as we just saw from Benjamin's talk, for example, in any actual implementation, usually we have to implement a coherent gate in order to implement a coherent, like measurement relative to a coherent basis. And we also heard from Sokyung Lee earlier about randomness as a resource. And if you think about it, if all systems are fundamentally quantum mechanical, then the only true source of randomness is coherence, arguably. So there are many sort of operational considerations for coherent measurement as a resource. In fact, there has also been a rigorous connection established between the distillation of coherence and the distillation of randomness in this work that includes Wang, who's here. Okay, so my project is specifically about the distillation of coherence and a certain hidden cost that's associated with distilling coherence. So let's look at the definition of asymptotic distillation. So here you're interested in mapping many copies of a given state rho to many copies of some standard coherent state. So here I've just taken this Hadamard state, which is customarily considered the standard. and you're interested in maximizing this rate R asymptotically. And it turns out that the maximum possible rate under the most general class of incoherent operations, the MIO class, is given by the relative entropy of coherence, which looks like this. But if you're limited to the SIO class, which, if you recall, where the Krauss operators cannot even detect coherence, then you can't really achieve this maximum rate. So this is work by Lamy and Bartosz and Adesso. So the question that motivates my work is, I'm sorry, yeah. So operationally, this implies that the ability of IO to detect coherence is critical in being able to distill coherence. And the question that motivates my work is, how much of this coherence measuring power do you need to distill? So in order to answer this question, I looked at a certain operator that I call the target witness. So if you have some desired target state psi, and you have a channel E, you just define this object called the target witness, and it's clear that it has this property that if you treat it as a kind of POV element, its expectation value for a given input tells you the probability that the channel E maps that input to the desired target. The nice thing about it in the context of coherence is that this object also captures the requisite coherent measurement structure involved in implementing E. So in a sense, the intuition for this is that this TE, it's a positive operator, and if you take convex decompositions of it into pure, like rank 1 components, then those decompositions correspond one-to-one with Krauss operator decompositions of the channel E. So the basic ingredients of all of my results are these two facts. So for a certain input rho to be mapped to the desired target, you require this target witness to act like the identity operator on the support of the input. And furthermore, the trace of this operator is constrained by various parameters appearing in the problem instance. So what I do is I define a density operator by normalizing this target witness. And then if you look at various coherence measures evaluated on the density operator, that gives you bounds on the coherent measurement cost of performing the desired state transformation. So among my results, I have some linear algebraic constraints on the structure of the coherent measurements involved in achieving certain state transformations, particularly distillation. Several lower bounds on the coherent measurement cost of distilling by the most general class of incoherent operations in the cases where the target is, in a certain sense, maximal, given the input rank and dimension. In the case where it's non-maximal, possibly also non-uniform. And finally, when the transformation is allowed to be approximate. And based on the approximate case, I have, so the bounds that I have apply, in fact, to any cross-operated decomposition of the channel. So even though, for example, MIO are not so well understood in terms of how to implement them, say through dilations or cross operators, the bounds that I find are applicable regardless of what kind of implementation you have. And based on these results, I have a conjectured lower bound on the coherent measurement cost of maximal asymptotic distillation. And I also conjecture that this bound can be achieved, in fact, by IO, which is a subclass of MIO. So I would like to talk a little bit about these conjectures. So in order to do that, we will take a little detour to some measures of coherence. So a while ago, I mentioned the relative entropy of coherence, which is defined in this way. And it turns out that it's actually conveniently described in terms of just the dephased state and the given state. And if you take the convex roof extension of the relative entropy of coherence, you get something called the coherence of formation. And both of these have operational significance in the resource theories of coherence. So for example, the CR, coherence, the relative entropy of coherence, is, as I mentioned, the maximal distillation rate under any of under the largest class MIO. And it is achieved by the IO subclass, but it is not by SIO, as we noted. CF, on the other hand, is the formation cost. So formation is like the opposite task of distillation. So if you try to take standard coherent states and turn them into copies of the given state, then CF quantifies the minimal cost in terms of the number of standard states. You can, so I find it convenient to define this quantity that I call the irretrievable coherence, which is a measure of the irreversibility under the IO resource theory. So it's just the difference between the coherence of formation and the relative entropy coherence. Okay, so now let's look at the asymptotic case of distillation, where I have the conjectures. In the non-asymptotic case, I have this result on a certain sense in which the distilled state is maximal. So if you have the input space being of dimension A, which means the number of symbols in the incoherent alphabet is A, and the rank of the input is S. And if you want to distill an n-fold coherent pure output where n satisfies this divisibility condition, then this a channel achieving this must involve coherent measurement over at least this amount of those many incoherent labels, where the argument of the argument here is the maximally mixed state on the support of the input, right? Okay, so if you look at the asymptotic limit, when you take n copies of rho, as n grows large, it can be approximated with something called the typical part, whose rank scales in this way, where the exponent is the Boltzmann entropy of rho. And it also starts becoming quite flat in terms of its spectrum. And then from similar arguments, the size of the alphabet on the n copy state scales like this. And the size of the distilled resource, as we noted before, is given by the relative entropy of coherence, which has this form. So approximately the conditions of this theorem seem to be satisfied in the asymptotic limit. And motivated by this, I have this conjecture that if you have a sequence of MIO channels that distill at the maximal rate from copies of a given input, then the number of coherent measurements involved must scale in this way, and where L is the irretrievable coherence that I mentioned before. And for slightly other reasons, I also conjecture that this rate of coherent measurement can be achieved by I/O. The reason for the converse conjecture is related to the distillation protocol that Winter and Young constructed. Okay, so what would be the operational implications if these conjectures were true? So think of what distillation does. So you have n copies of rho, and there's some channel that you apply to it, which may here and there involve some coherent gates. And then in the end, you get something that's equivalent to preparing a certain number of small n of standard coherent states. Now, if it so turns out that the small m is smaller than big M, then you can do the following. You can just take the given copies of the input, toss them in the trash, and then you just prepare big M fresh Hadamard states from, if you're going to use big M Hadamard gates anyway, so you might as well just prepare those many fresh coherent states. So it's arguable that if there are instances where this small m is smaller than big M, and if my conjectures hold, then it brings into question the usefulness of distilling coherence in these cases. And indeed, I looked at some examples just on qubit states. So here's just a representative sample of qubit states, and on the x-axis is just a parameter about that describes the purity of the state, and on the y-axis you have the conjectured excess cost in terms of coherent measurements, meaning whatever values are above zero on the y-axis, that's like saying you use more Hadamard gates to distill than the number of Hadamard states that you distill in the end. And in fact, the plot on the right side shows like the same thing, but divided by the yield, like divided by the number of Hadamards that you distill. So you can show that you can choose parameter values to make this ratio arbitrarily large. So there are regimes where you use like an arbitrarily large multiple of the yield that you distill in terms of coherent measurements. Okay, but of course, all of this is conjectural. So let's look now at, sorry, I also have some speculations about an asymptotic trade-off between the coherent measurement and the distilled yield. So if you're prepared to not distill maximally, then it's possible that you can trade off some rate of distillation in order to reduce the cost of coherent measurements. Okay, so now let's look at what happens, what are the problems that prevent the conjectures from going through. So ideally, I would have wanted the coherent measurement cost to be like one of these measures, like the CR or CF, evaluated on the input itself. So for example, if you just abbreviate them as C, they both have this property that they're additive under tensor products. So if you have C of n copies of rho, that's just n times C of rho, and that would be super convenient. But what actually happens is the coherent measurement cost involves these measures quantified on some object tau n that kind of smells like n copies of rho, in that, for example, it comes from this kind of witness operator that has a high degree of overlap with the support of rho n. And there are various constraints that if you stare at these, it kind of motivates the intuition that you would expect the density operator tau n to become quite similar to rho n in the asymptotic limit. So what I tried to use to prove the conjecture was asymptotic continuity of these measures, but that requires that this tau n approaches rho n, in terms of fidelity, for example. What we actually have is that these constraints are not quite enough for the fidelity to converge to 1. Instead, they're just about strong enough to prevent the fidelity from decaying to 0 too fast. So in a sense, these tau n's, the sequence of tau n and rho n, they're not like generic pairs of states, because in a sense they're trying to stay close to each other. Their fidelity cannot decay exponentially to 0. So this gives me some hope that maybe the conjecture can be proved through some other methods. So for example, there might be a modified version of asymptotic continuity that applies for some special sequences of states, because they're not generic and they have some specific relationships with each other. I also speculate that there might be some kind of asymptotic equipartition for these convex roof coherence measures. So if you define, for example, coherence measures based on the alpha Rényi entropies for pure states, and then something similar to that for mixed states, where you have a convex roof extension, but now the convex decompositions that you take are not of rho itself, but of something proportional to a power of rho. And if it turns out that after some appropriate smoothing, you have some kind of asymptotic equipartition of these measures, whereby they all in the asymptotic limit start looking like the coherence of formation CF. That might help settle these conjectures. It's also possible that you can look at the asymptotic behavior of certain monotones that Ludovico Lamy calls mu k in his work. And also in the same work, Lamy uses some kind of classical information encoded in the coherence of a state, and sort of the asymptotic information theory of that classical variable centrally features in his results on SIO distillation. So it's possible that there's a connection there. In summary, we have a way of characterizing the coherent measurement cost of implementing a channel using a simple linear algebraic construction. We use this construction to get lower bounds on the coherent measurement cost for distillation in various cases. We conjecture that in the asymptotic limit for maximal distillation, the number of Hadamard measurements scales linearly in the number of input copies, and that the rate of the cost, the exponent that appears, is a measure of the irreversibility of the I. sorry, IO resource theory. We also conjecture that this rate can be attained by IO. And we have proof sketches for both of these conjectures that you can find in the paper that I'll share soon. The main impediment to these proofs going through seems to be coming from a very demanding version of asymptotic continuity, which requires the pairs of states to actually become close in terms of fidelity. For the future, I hope that these conjectures can be settled either through modifying the asymptotic continuity property or finding some kind of equipartition property for these convex roof measures, or through Lami's mu-k monotones, or possibly other methods. But apart from the conjectures, there are also other research avenues. For example, what I mentioned about classical information encoding and coherence distillation. Could there also be similar constructions for sort of dual costs of various tasks, which is like some kind of dynamical cost, but it's not quite like resource generation cost. It's more like resource witnessing cost of implementing certain tasks. Can we do this for other resource theories? And are those dual costs related somehow to reversibility or irreversibility, which was the subject of Bartosh's talk? With that, I thank the organizers and thank you all.
Yeah, thanks. Any questions? Questions? Okay, I guess everybody's hungry and everything is clear. Yeah, thanks again, Varun.